Right now, there is a boundary sitting a few trillion kilometers away that no human being will ever cross. Not because we haven't tried hard enough, but because the laws of physics themselves may have already ruled it impossible. And the strangest part is this: we didn't discover this wall by launching a probe into it. We found it sitting quietly inside the math. What is this barrier made of nothing but distance, radiation, and dust? And why does the universe seem almost deliberately built to keep us sealed inside it? Stay with this, because by the end you'll understand why the same physics that lets us see every star in the night sky might be exactly what stops us from ever touching one. Your brain cannot actually process how big this problem is. It was never built to. It evolved to judge the distance to the next tree, the next river, the next meal. So when someone tells you a place is very far, and then tells you another place is 1,000 times farther, something quietly breaks in your head. Both statements just register as very far away. But the gap between those two distances is the entire reason this video exists. Let's replace that broken intuition with real numbers. The fastest human beings have ever physically traveled is 39,897 kilometers per hour, reached by the crew of Apollo 10 on May 26, 1969, weeks before the moon landing. That's roughly 32 times faster than a commercial airliner. Impressive. Still catastrophically slow. The fastest object humanity has ever built is NASA's Parker Solar Probe, which on December 24, 2024, swept within 6.1 million kilometers of the Sun's surface and hit a top speed of 635,266 kilometers per hour, borrowing energy from the Sun's own gravity well. At that velocity, you could circle the entire Earth in under 4 minutes. Now, hypothetically, strap a human crew onto something that fast and pointed away from the Sun. Mars becomes a 2-week trip, compared to the 7 to 10 months required by today's chemical rockets. Pluto is just over a year away. Voyager 1, the most distant human-made object in existence, currently sits roughly 24.5 billion kilometers from Earth. After 47 years of continuous flight, our ship catches up to it in just over 4 years. This is starting to feel almost easy. Then comes the real edge of the solar system, and everything changes. Beyond Pluto, beyond Voyager, lies the Oort Cloud, a shell of icy debris starting around 2,000 astronomical units out and stretching to roughly 100,000 astronomical units, nearly a light-year and a half from the Sun. At Parker, solar probe speed, reaching its outer edge, takes approximately 2,700 years. That's longer than the entire combined histories of the Roman Empire, the Ottoman Empire, and the Ming Dynasty. And when your descendants finally arrive, 27 centuries after launch, there is nothing there to greet them. No planet, no light, no signal, just ice and silence, and the terrible realization that you haven't even left home yet. This is the first barrier. Distance so extreme that our fastest machine, the product of 70 years of rocket science, needs 3 millennia just to clear our own front yard. And that's before traveling a single meter toward another star. So the obvious response is, build something faster. And theoretically, we can, up to a point. Nobody has built a warp drive. Faster-than-light travel is still explicitly forbidden by Einstein's field equations. Nobody has frozen a human being into functional suspended animation for a century. But some real, non-magical propulsion concepts exist on paper. In 1958, the United States seriously investigated Project Orion, a spacecraft propelled by detonating small nuclear bombs behind itself, theoretically capable of reaching 10% the speed of light. In 1978, the British Interplanetary Society designed Project Daedalus, a 2-stage fusion-powered probe weighing 54,000 tons, almost entirely fuel, meant to ignite pellets of deuterium and helium-3 with electron beams and cruise at 12% light speed. In April 2016, billionaire Yuri Milner and physicist Stephen Hawking announced Breakthrough Starshot, a plan to fire a theoretical 100-gigawatt laser array at gram-scale probes riding thin reflective sails, accelerating them to 20% light speed in minutes, aimed at Alpha Centauri. Let's be generous and assume humanity eventually builds a crewed ship that reaches 20% the speed of light, 60,000 kilometers per second, 216 million kilometers per hour. Quick correction to your sci-fi instincts. At that speed, time dilation is real but tiny. The Lorentz factor at 20% light speed is only about 1.02. The crew ages barely 2% slower than everyone back home. No shortcuts there, but the raw speed still helps enormously. The outer Oort Cloud, once a 2,700-year sentence, now takes about 8 years. Alpha Centauri, the nearest star system to our own, drops from an impossible 10,000-year crawl to just over 20 years. For the first time in this story, it looks almost solvable. It isn't. Space looks empty. It is not empty. Interstellar space still contains roughly 1 atom per cubic centimeter, scattered dust grains left from dying stars, and the occasional pebble drifting since the birth of the galaxy. At normal cruising speeds, this is irrelevant. Spacecraft fly through it for decades without a scratch. NASA's Stardust probe flew directly through the coma of Comet Wild 2 in January 2004 at 6.1 kilometers per second and survived with nothing more than a simple foam and mesh Whipple shield. But at 20% the speed of light, you are moving roughly 10,000 times faster than Stardust was. And physics does not scale kindly with speed. A single iron atom striking your hull at 60,000 kilometers per second carries enough kinetic energy to carve a damage track 1/10 of a millimeter deep. Multiply that by trillions of impacts across a multi-year voyage, and your hull becomes riddled with microscopic bullet holes at the atomic level. Engineers can bolt on a thick sacrificial shield of graphite or beryllium to absorb most of this. But dust is far worse than atoms. A 2017 study by astrophysicists Thiem Huang, Alex Lazarian, and Abraham Loeb calculated that a single interstellar dust grain, roughly the width of a human red blood cell, hitting a relativistic spacecraft at 20% light speed, detonates with the destructive force of hundreds of millions of times its own mass in TNT, instantly vaporizing whatever shielding it touches. And dust isn't even the worst case. Hit something the size of a golf ball at that speed, and the collision releases more energy than the atomic bomb dropped on Hiroshima on August 6, 1945. There is currently no known material, no shielding design, no clever engineering workaround that reliably survives an impact like that at relativistic speed. This isn't a gap in our technology. It's a wall imposed by kinetic energy itself, which scales with the square of velocity, meaning every extra fraction of speed we gain to save decades of travel makes every rock in our path exponentially more lethal. We may have already found our practical speed limit. It wasn't set by ambition, it was set by a grain of sand. Let's say we accept the risk, shield what we can, and launch anyway. There's a third barrier, and this one doesn't attack the ship. It attacks the crew. When Voyager 1 crossed the heliopause on August 25, 2012, the boundary where the sun's solar wind finally gives way to interstellar space, its instruments recorded something chilling in real time. Galactic cosmic ray counts spiked sharply, while solar particle counts collapsed. Outside the protective bubble of our star, deep space is bathed continuously in high-energy particles flung across the galaxy by exploding stars, indifferent to whichever fragile species happens to be passing through. NASA's Curiosity rover carried a radiation detector called Ray-D during its 253-day cruise to Mars in 2011 and 2012, and measured a dose that would expose a round-trip astronaut to roughly 660 millisieverts, equivalent to a full-body CT scan approximately once every 5 days, for 8 straight months. NASA caps a career astronaut's lifetime radiation exposure to keep added cancer risk under roughly 3%. A multi-year voyage to another star, with no magnetosphere and no atmosphere to hide behind, blows past every existing safety threshold, unless the crew hauls shielding heavy enough to defeat the entire purpose of building a fast, lightweight ship in the first place. Picture it for a second. Day 7,300 of the voyage. No new stars have grown any closer looking. No message from home has arrived in 11 months. And every cell in your body is quietly accumulating a radiation debt no doctor on Earth signed off on. Astronauts aboard the International Space Station lose bone density at roughly 1 to 1.5% per month in microgravity. According to NASA studies published from 2004 onward, a rate of loss elderly osteoporosis patients experience over an entire year. Muscle mass, cardiovascular strength, and eyesight all degrade during long stays. The psychological toll is just as documented. In 2010 and 2011, the Mars 500 project sealed 6 volunteers inside a windowless simulated spacecraft in Moscow for 520 days, and crew members reported depression, sleep disruption, and conflict, despite knowing the entire time that the exit door was 1 hallway away. Now stretch that isolation from 520 days to 20 years, or 200, which surfaces a problem almost nobody thinks about until it's too late. You can't send one hero. You need a self-sustaining, breathing ecosystem. In 1991, scientists in Oracle, Arizona, sealed 8 people inside a 3-acre glass structure called Biosphere 2, engineered to recycle its own air, water, and food indefinitely. Within 16 months, oxygen levels had fallen from a safe 21% to a dangerously thin 14%, equivalent to the air at 4,500 meters altitude, and crops began failing unpredictably. That experiment had sunlight, Earth's gravity, and an emergency exit door. A generational starship would have none of those luxuries. Even if the ecosystem holds, there's a colder mathematical wall waiting behind it. A 2013 peer-reviewed study modeling a multi-generational voyage toward Proxima Centauri concluded that a founding population smaller than roughly 98 people would likely collapse from inbreeding and genetic drift within a few centuries. Many researchers now argue the real safe minimum is closer to several hundred, possibly thousands. Read that number again. You're not building a spacecraft anymore. You're building a nation, sealed inside a tube, that has to stay genetically viable and psychologically intact for longer than most actual nations in human history have managed to survive. And suppose every one of those problems gets solved. There's still the loneliest barrier of all: silence. At Alpha Centauri, 4.24 light-years from Earth, a message sent home takes 4.24 years to arrive, and the reply takes another 4.24 years to return. By the time you hear an answer to a simple question, over 8.5 years will have passed back home. Elections will have come and gone. Technologies will have become obsolete. Anyone you left behind who wasn't young when you departed may already be gone by the time your "we made it" message reaches them. You wouldn't just be far from Earth. You'd be talking permanently to Earth's past, in a conversation that can never, ever catch up to the present. Here's the twist that turns the whole mission almost tragic. Even if you survive everything above and cross those 4.24 light-years, the destination itself might not be worth it. Proxima Centauri b, discovered in August 2016 by the European Southern Observatory, sits in its star's habitable zone at roughly 1.07 times Earth's mass, but it orbits a red dwarf prone to violent flares. In 2021, astronomers using Hubble and ALMA recorded a flare that made the star briefly 14,000 times brighter in ultraviolet light, an event that would likely sterilize any unshielded surface. TRAPPIST-1, a system 39.6 light-years away discovered in 2017, has 7 Earth-sized worlds, several inside the habitable zone, but current models suggest most are tidally locked, forever showing one scorched face to their star, atmospheres likely stripped away over billions of years. Teegarden's star B, just 12.5 light-years out, and confirmed in 2019, is Earth mass and technically habitable, but we have no confirmed data on whether it even keeps an atmosphere. We are choosing potential graveyards for humanity's greatest journey, almost entirely blind. Zoom out far enough, and the picture gets bleaker still. Even our most optimistic propulsion concepts only make destinations reachable within a human lifetime if they sit within roughly 8 to 10 light-years of Earth. That bubble, a sphere representing about 0.0000002% of the volume of the Milky Way, contains fewer than 3 dozen known stars. Only 3 of them closely resemble our own Sun, and one of those 3 is the Sun. The rest are almost entirely dim, volatile red dwarfs, the most common but least hospitable class of star in the galaxy. We built humanity's entire cosmic dream on the assumption that out there is packed with destinations. It might just be packed with distance. So maybe humanity never leaves. Maybe the numbers simply refuse to bend, no matter how much time or money or genius we throw at them. But before you accept that as the final word, remember something the smartest people alive have gotten catastrophically wrong before. In 1895, physicist Lord Kelvin declared that heavier-than-air flying machines were physically impossible. In 1901, astronomer Simon Newcomb wrote that no combination of known substances and mechanisms could ever be united into a practical flying machine. 2 years later, on December 17, 1903, Orville Wright flew 36.5 meters in 12 seconds at Kitty Hawk, North Carolina. 66 years after that, in July 1969, human beings walked on the moon. The gap between physically impossible and routine Tuesday has collapsed faster, again and again, than the smartest people alive were ever willing to admit. So maybe fusion propulsion becomes practical within a century. Maybe medicine slows human aging enough that a 200-year voyage feels like a long commute instead of a life sentence. Maybe artificial wombs and AI caretakers let us send frozen embryos instead of adults, arriving generations later, with nobody aboard who ever remembered leaving Earth. Or maybe, and some serious scientists believe this, the entire premise is backward. Maybe the next chapter of our species was never meant to unfold out there, gambling everything on one fragile, radiation-blasted tube crossing a hostile void for centuries. Maybe it's meant to be built here, inside the solar system we already own, beneath the ice oceans of Europa, inside the sulfuric clouds of Venus, inside minds and machines we haven't invented yet. That's a story for another day. For now, sit with this. Every star you can see with your naked eye tonight is, for all practical purposes, permanently sealed off from us. Not because we lack courage, not because we lack curiosity, but because the universe placed a wall of pure, unglamorous physics between us and them. Distance too vast to cross. Speed too dangerous to reach. Bodies too fragile to survive the trip. Destinations we can't even confirm are worth reaching. And yet, somewhere between Kelvin's confident impossible and Kitty Hawk's 12 seconds of flight, there's a lesson we keep refusing to learn. The walls that look most permanent are usually the ones about to fall. Subscribe, because the next video is about the one idea serious physicists think could actually break this exact barrier, and if it works, you'll be able to say you saw it explained before the rest of the world caught up.